By the end of this video, you should be able to 1. Propose how Bohr's theory explained the line spectrum of a hydrogen atom based on the experimental data collected in earlier studies. 2. Calculate the energy and the wavelength of the photon absorbed or emitted when a one-electron system experiences a change in energy level. This is what we do to obtain the line spectrum of a hydrogen atom. We take a sample of hydrogen gas and pass electric discharge through the sample. The hydrogen molecules first break into hydrogen atoms. These hydrogen atoms absorb energy from electric discharge and get excited. The excited hydrogen atoms are unstable and emit radiation consisting of discrete energies. We pass this electromagnetic radiation through a prism. As we learned earlier, the prism separates the electromagnetic radiation into individual wavelengths. We then expose the light coming out of the prism onto a photographic plate or recorder. We get a pattern which contains bright lines on the dark background. This is called the atomic spectrum of hydrogen. The line spectrum of the hydrogen looks like the following, with 4 discrete bright lines starting at 410 nanometers up to 656 nanometers on a dark background. The next question was why the emission spectrum of the hydrogen, or for that matter any other atom, shows discrete bright lines on a dark background. Why doesn't it show a continuous spectrum like the white light? Very soon, the scientists started realizing that the line spectrum of the atoms gives us a great deal of information about the electronic structure of the respective atoms. In the next few topics, we will learn the theories that used the line spectrum of atoms to explain its electronic structure. The first attempt came in the year 1885. Johann Balmer discovered a mathematical relationship to describe all the lines in the visible region of the hydrogen atomic spectrum. The relationship was the following. 1 over lambda is equal to r times 1 over 2 square minus 1 over n squared. Where r is a constant, its value is equal to 1.097 times 10 to the 7 meter inverse. And n is an integer value greater than 2. It can have values from 3, 4, 5, 6 and so on. For each value of n plugged into the equation, we get a corresponding value of wavelength in the hydrogen atomic spectrum. For example, for n is equal to 3, we get lambda is equal to 656 nanometer, and for n is equals to 4, we get lambda is equals to 486 nanometers, and so on. This is just a mathematical relationship that Balmer came up with based on the experimental data. He did not provide any explanation of how the lines on the atomic spectrum are related to the electronic structure of the hydrogen atom, nor did he provide any theoretical background supporting his mathematical relation. The series of lines described by this formula are usually referred to as Balmer series of lines. All these lines are in the visible region of the electromagnetic spectrum. Few years later, scientists found that there are more lines in the hydrogen atomic spectrum that are outside the visible region of the electromagnetic spectrum. As you can see, there are several lines in ultraviolet region and infrared region of electromagnetic spectrum as well. Later, Johannes Rydberg modified the equation given by Balmer to describe all the lines in the entire spectrum of hydrogen atom. Rydberg's formula is 1 over lambda is equal to z square times r times 1 over n1 square minus 1 over n2 squared, where the z is the atomic number of the atom, n1 and n2 are integers just like what Balmer proposed, except for the condition that n2 has to be greater than n1. The spectral lines in the hydrogen atomic spectrum are classified into several series based on the value of n1. For n1 is equal to 1, the possible values of n2 can be 2, 3, 4, and so on. Each combination of n1 and n2 values gives a line on the emission spectrum of hydrogen. For example, the rightmost line in the visible region has n1 value is equal to 2 and the n2 value as 3. This we have seen in the Balmer's equation. All these lines with n1 is equal to 1 appear in the UV region and are called as Lyman series. For n1 is equals to 2, the possible values of n2 are 3, 4, 5, and so on. The Rydberg's formula is now reduced to Balmer's formula, and we know that the corresponding lines are in the visible region and the name of the series is called as Balmer series. For n1 is equals to 3, the n2 values are 4, 5, 6, and so on, and the lines appear in the infrared region of electromagnetic spectrum. These series are referred to as Paschen series. Similarly, n1 is equals to 4, the n2 values are 5, 6, 7, and so on. They still appear in the IR region, and the name of the series is bracket. For n1 is equals to 5, the n2 values are 6, 7, 8, and so on. They appear in the IR region, and the name of the series is fund. Even though Rydberg's formula could describe all the lines on the hydrogen atomic spectrum, there was no theoretical background for this mathematical relationship, and he did not provide any information on the electronic structure of the hydrogen atom. Niels Bohr was the first person who put all these things together and came up with a model of the atom that explains the electronic structure. We will discuss the Bohr's model of hydrogen atom in the next video.